Okay, so this is a video we're going to take a look at momentum and then we're going to move on to look at impact forces and that sort of thing. So let's start off right at the beginning and discuss how we calculate momentum. If you know quite a bit about momentum, it might be more beneficial to you to skip towards the end. But I'm going to start from the basics. So how do we calculate momentum? Well, your momentum, which we often refer to as P, is mass times the velocity of an object. So we've got this ball here that's moving at 2 meters per second, and the mass of the ball is 3 kilograms. So obviously your P, substituting numbers, to 3 kilograms times 2 meters per second, which equals 6 kilogram meters per second. Now, that's one of the units of momentum, and I'm just going to take a quick side note here because you might sometimes see another notation for the unit of momentum. I'm going to write this at the top right. Another possible one would be in Newton seconds, and I'll explain how we get to that. So think about a Newton's force. We calculate force using our F equals ma equation. So the units of a Newton would be a kilogram, which is your m, times by the units of acceleration, which is meters per second minus 2. And if we look down the bottom, we've got kilogram meters per second. So if we multiply this kilogram meters per second by second, this minus 2 becomes minus 1, which is what we have on the bottom. So a Newton second is exactly the same as a kilogram meters per second. And they are two different units of momentum, and you should be able to recognize both of these. Okay, let's move on. So quite a lot of examples you might come across. You might say have two balls, one's moving, one's not, or the other one could be moving, and you're asked to find out what happens after they have collided. Now, in order to apply any equations to this, you need to apply a principle of conservation, and the principle of conservation you need to use is conservation of, I'm going to write this in capital because it's really important, momentum. Momentum must always be conserved. This is one of the key principles, like we've talked about how energy must always be conserved, or in some of the AS you looked at different properties needed to be conserved. This one, we're all about the conservation of momentum. So in order to find out how the balls are going to behave after a collision, you first need to know what their state is before the collision. So let's work out what the momentum is before the collision. So the one on the left, we've got the momentum is 3 times 3. And obviously, considering the one on the right, you've got 0 times by 2. Gives you a total of 9 Newton seconds. So that's momentum before. So we know that this must be equal to the momentum after. Now, in these questions, what they can do is they can either tell you that the two balls stick together afterwards, so they behave as one object, or they can tell you the momentum of one of the objects, and then you have to work out the momentum of the other one. So in this example, I'm going to assume that these balls then stick together and travel together, which you might think is a bit odd, because balls don't tend to do that, they don't tend to stick together. But for this case, we're going to assume that they do. So if we assume they stick together, then the total mass left would be 5. Okay, so what you know is that the momentum, which we obviously calculated must be 9, is equal to the total mass, if they stick together, which would be 5, times by whatever the velocity is. So then, obviously, you rearrange those to get the velocity is equal to 9 over 5, which is equal to 1.8 meters per second. And of course, this has come out as a positive number, which must mean the final object is moving to the right in the same direction as the original balls. So that's considering that both balls stick together. Now I'm going to have a look at an example where they don't necessarily stick together. We've got some bit more movement going on. Okay, so in this example we've got a ball moving to the right, we've got a ball moving to the left, and in this case what we're going to do is we're going to say that after the collision, ball 2 travels at 1 meter per second to the right. So that's the information you need to solve this question. Okay, so first of all, we've got velocities going in different directions, so we need to define a positive direction for velocity. And by convention, we usually say to the right is positive. So I'm going to draw that up on the top right and say it's positive to the right. Oh, that's got really messy. Let's clean that up. So we've got positive to the right. Okay, so let's consider the momentum before the collision. Okay, so for this one, we've got 3 times 3. Obviously, we add the momentums together, and we've got velocity, but it's in the opposite direction, so it would be minus 2 times 2. So we end up with 9 minus 4 is equal to 5 Newton seconds. Now, we're not going to assume that they stick together this time, but what you have got is information that ball 2, that's the one on the right, I should have made that more clear, is going to be going at 1 meter per second to the right. So we know total momentum is equal to 5. So whatever the momentum of the two objects is afterwards, it must add up to 5. Now we know the mass of ball 1 is 3, but what we don't know is its velocity, so I'm going to call that v. And then we're going to, because it says to the right, we know we're going to have a positive number 1 times by 2. Okay, so what we got is 5 equals 3v plus 2. So if we rearrange that, we've got 3v equals 5 minus 2, which equals 3. Oh, this has come out really nicely. And that must mean that v is equal to 1 meter per second. That's come out as a really nice number, which is great, because considering I picked the numbers from at random. But anyway, the same steps will work for any number, and you obviously might end up with a not nice number. But you apply the same principles and you should be able to solve any situation. Okay, so let's rack up the difficulty a little bit. Instead of a ball, what we've now got is a wall. Now, what's going to happen is obviously we've got our ball coming in, it's going to collide with the wall, and then it's going to basically go off in the opposite direction. So, thinking about what I talked about in the last video, Newton's third law, when two objects interact, they exert equal and opposite force on each other. So what's going to happen is the momentum of the ball is going to change. So the momentum currently is going to the right, and it's going to end up going to the left. So you must have had a force acting on it to cause its momentum to change. So the wall must have been exerting a force on the ball. By Newton's third law, that must mean the ball is exerting a force on the wall. Which obviously, if that force is big enough, you might start to think, well, is that damaging the wall if we're applying force, that sort of thing. And the equation we need to know at this point is the force of an impact is going to be equal to your change in momentum. So your change in momentum over the time the impact occurs. You might think, well, the ball is just going to come in and bounce off. There's not going to be really much time involved in the momentum change. But it's not quite as simple as that, because if you load up some slow-mo videos of balls hitting things, even something really hard like a golf or a baseball, what you actually see is when this ball hits the wall, so we're going to run it in, what you'll actually find is you still get the round on this side coming in, but it completely flattens out against the wall. There's actually quite a period of time that the ball is in contact with the wall, which actually means if you lengthen the time, the momentum change is going to be the same, so you actually have a smaller amount of force on the wall. So that's why when you're playing squash or something, you don't actually see yourself damaging the front wall, because actually the force doesn't end up being that big. But anyway, I'm digressing slightly. Let's get back to this. Okay, so what I'm going to say is the ball's going to come in, it's going to hit the wall, it's going to be a bit squashed on there, and then it's going to bounce back. And I'm going to say this is something we're going to come on to later, a perfectly elastic collision. So I'm going to say the speed going in is going to be the speed going out, because no energy is going to be lost doing all these sorts of bouncing motions. We'll find out that's not actually the case, but it's quite a useful assumption at this point. So that means that when it leaves the wall, it's going to be travelling at u meters per second, but it's going to be in the opposite direction. Okay. So, like I said before, first thing, let's define our positive direction. So I'm going to say it's to the right. So first of all, if we want to calculate the impact of the ball on the wall, we need to know what the change in momentum is. So let's do that. So the mass isn't changing. We're not doing some sort of nuclear physics. It's not a rocket. It's a ball, so it's going to have the same mass. Okay. So the mass is going to be the same. So momentum change, initially it's going to be u, so v, and the change in it, so we're going to subtract, and then obviously if it's going in the other direction, it's minus u, and obviously we're going to be interested in the time taken. So this is what we want, the force of the ball on the wall, and we've got this situation here, and u minus u is u plus u, so you end up with 2u times m T is your force on the wall, given that that was the speed going in and it's the same speed going out. Okay, so what's that actually going to look like if we plot this graphically? And things are going to get a bit jumbled up here, but I just want to clear them out of the way so we don't need those anymore. If we sketch our axes like before, so we had force and time, with this sort of impact, what you'll actually see is you'll get something along the lines of this. So obviously you got your time, your impact time along here at the bottom, and you'll see how the force changes in that. And obviously the change in momentum, as we said before, is going to be the area under this graph. So this is what a real impact of something would look like. It's not quite as cut and dry as we'd like, but if you plotted the graph of the force of the ball against the wall and the time, you'd see something a bit like this. Okay,